now that you've seen the first set of advanced completable future features, namely the factory methods that start everything in motion, let's talk about the really cool part of this. And that portion is the portion known as the completion stage methods. And as you can see, the completion stage methods form the bulk of the completable future API. Remember, there's like 60-some methods in one class, so it's a rather large surface area, but about 40 of them are completion stage methods. And what these do is they chain together actions that process the results of asynchronous computations and also allow composition of results in various flavors, as we'll see in a second. So what's the point? The point is that a completable future, among other things, can serve as a completion stage for processing the results of asynchronous computations. And in fact, there's actually another interface which completable future implements called completion stage, which you can take a look at here. If you're really interested in learning about completable futures and the completable future framework, I strongly recommend you read this page. It's got a wealth of great descriptions of what all the different methods do. I'll walk through a lot of them, but if you need more thorough discussions, more comprehensive discussions, that's a good place to go to find out more information. So what does this all mean? What is a completion stage? It means that an action will be performed when an asynchronous operation completes. So the action will be performed on the result of an asynchronous computation when that asynchronous computation has finished running asynchronously. Okay, so far so good. So let's take a look at an example. Here we're going to define ourselves a variable called unreduced, which is a big fraction, and we're going to basically make an unreduced big fraction with this numerator and this denominator. So we have an unreduced big fraction. That means it's not been reduced to its reduced form. We're then going to go ahead and define a supplier local variable called reduce, and the lambda expression for this is going to say, take the unreduced big fraction and reduce it. Okay, so far so good. Now what we're going to do is we're going to go ahead and first call supply async with reduce, so that's this thing here. So we're going to go ahead and reduce this big fraction. And then when that's done, when the asynchronous operation that's reducing this big fraction finishes, in other words, when the action reduce passed to supply async completes, then we will apply this operation, which will take the reduced big fraction and convert it to a mixed string. So it takes an improper fraction and makes a mixed string out of it. But this action here only runs when this previous action completes. So that's what makes this a completion stage method. It completes only when the previous one is finished. And we can actually chain these things together in a Fluent style. So you can see that after the computation runs asynchronously, we've reduced it. We then convert it to a mixed string. And then we take that mixed string and we print the mixed string out. And this way of writing code with an operation dot another operation dot another operation is commonly known as the Fluent interface API design pattern. And you'll see this used over and over again in all kinds of things. What you often don't see it used, however, is in an asynchronous context, which is what this is showing. So what's happening here is each of these completion stage methods, supply async, of course, is a factory method, then apply and then accept our completion stage methods. What they're doing is they're registering lambda actions to apply or to perform when the previous stage completes. And a given action is only called when the action at the previous stage that's running asynchronously has finished and has yielded a result. That's kind of the way to think about that. So you can basically see these as essentially deferred computations that are registered with the framework to be called back when, in this case, a previous stage completes. And there's a fork join pool ready and able to process the results. Any questions about that? It's a little bit deceptive. It's actually, once you get used to it, it's quite simple and easy to understand. But when you first look at this stuff, it's a little bit confusing because it's not really clear that these things are only running when the thing ahead of it finishes asynchronously, right? Because it looks almost like they're being applied synchronously, but they're being applied as the result of asynchronous computations. So why the heck do we do all this stuff? Completion stages are valuable in the Completable Futures framework to avoid blocking threads until the results absolutely must be obtained. So you really don't want to have to block unless you really, really, really have to. So we don't want to block as a general rule of thumb. So one of the consequences of this, which you should always remember when you're writing asynchronous code with this framework, is try to avoid calling join or get unless you absolutely, absolutely must. So you really try to avoid doing this. And in many cases, if you're writing a server, if you have computations that are running on the server side, where there's no direct user interface, where there's no user kind of waiting for something to show up, at least not directly, you don't even have to call join. You can just start things running asynchronously, and they do their computation, and when they're finished, the result will be sent back to the client. In some cases, however, client code may actually need to call join, at least once, because oftentimes you start some computation running on the GUI, and you need to get that result, and you need to get it back to the user eventually, so you may have to join it. I'll show you some examples of the latter with the clients called join as we look at more complicated examples. The purpose of this is to help improve responsiveness. Remember we talked before about the reactive programming principles of the reactive manifesto, and one of them was responsiveness. And so avoiding blocking is a way to make things more responsive by avoiding waiting. So you'll be running computations in the background rather than blocking. The metaphor I like to think about when I'm thinking about these features are basically juggling. So if you think about what completable futures are doing, the goal, as with juggling, is to keep the balls in the air, right? You keep the ball synchronously in your hand just long enough to throw it back up in the air, right? And if you're really good, you can keep multiple things going. Same idea with completable futures. You want to keep as many things going on asynchronously as possible and only grab them, hold them long enough to initiate the next asynchronous operation. So it requires kind of rethinking about the way things work. All right, so we're about to talk about how to group things together with completion stage methods. But before we do that, you might want to go see Robert, because I think he is right there. So I will see you a little bit later. OK, what we're going to do now is we're going to talk about grouping completable future completion stage methods together. And this is really interesting. This is, for my money, this is the most interesting part of completable futures, is the stuff we're about to talk about right here. So it turns out that of these 40 or so methods that are part of the completion stage portion of the API, there are so many of these methods that we also have to further classify them, right? So we've already classified things to have factor methods, basic methods, which we've talked about, exception methods and arbitrary arity methods, which we haven't talked about but will, and completion stage methods. And as you can see, the completion stage methods are so plentiful that we have to further decompose them into several categories as well. And the categories are going to be based on what you have to wait upon in order for the next completion stage to trigger, to run. And we'll see that there's 3 different variants. A bunch of the methods just wait for the completion of a single previous stage. There's some other methods that wait for the completion of 2 previous stages where both have to complete. And there is yet another set of methods that wait for either of 2 previous operations to complete. So you'll see there are 3 different groups of these things. And then you'll also see that they're even further decomposed by whether or not the results of a previous operation run in the same thread as the part that came before, or whether it can run in a different thread. So there's many different cross-cutting orthogonal dimensions that make the API cumbersome to understand, although once you understand it, it's pretty simple, but there's lots of moving parts at first. So we're first going to take a look at the methods that are going to be used, they're going to be triggered with the completion of a previous stage. So these methods, the ones that are the non-async ones, I'll explain what the async ones mean in a second, they run either in the invoking thread, the thread that called this thing, or more commonly, in the same thread as the thread that just finished computing the previous stage. So that's the non-async methods. And you can see there's a bunch of these. Then apply, then compose, then accept, then run. I'm not going to talk about them right now because I'm going to go through each of them one at a time and explain them to you. This chart is just here kind of as a single place to go to find a synopsis of what they do. So you can see that they take different kinds of parameters. You can see they have different kind of return values. You can see what they have different kinds of behaviors. I'll talk through all those things. Yes? So within a give, so the question is, how are the completion stages called? For a given asynchronous computation, keeping in mind you could have multiple asynchronous computations running in parallel. But for a given asynchronous computation, what would you think the answer would be, based on what we just talked about? What do you think the semantics are? If I have, I'll show you a specific example to make it more clear. Let's go back over here a ways. Let's take a look at, whoops, now I've done it. There we go. Okay, try this again. So let's say that we've got this particular example here. Supply async, then apply, then accept. You tell me, how do you think these completion stage methods are going to be called? Exactly. So they're run one after another, right? So you first do, I think I show it here. So a lambda action, reduce, big fraction, colon, colon, a mixed string, system.out, colon, colon, println. A lambda action, which are these things in red, are called only after the previous stage completes successfully. So it's done one after another. But each of the computations run asynchronously. And of course, as we said before, you could have multiple asynchronous computations taking place in parallel. But a given computation will, of course, run in a sequential order with the completion of asynchronous operations that came before. Yes? Good question. So I think the question that you're asking is, remember with the stream, when we had Java 8 streams, we had these sort of intermediate operations, and nothing began until you hit the terminal operation, and then all the wheels started. Things work a little differently with completable futures. So this thing is actually initiated as soon as supply async is hit. So it's going to go ahead and start running this reduce computation in a background thread. When that's done, then apply will be called. When that's done, then accept will be called. So there's no notion of a terminal operation here the same way there is with a stream. Because a stream, a classic stream, even a parallel stream in Java, is a pull abstraction. So you're pulling the data from a source through a bunch of intermediate operations until you reach a terminal operation, and then you do something with the result. You reduce it somehow, for example. Completable futures, in contrast, are pushing through computations asynchronously and then having something called back when they finish. So there is no, the terminal operation here is simply whatever is the last thing in the chain. But it's not terminal in the same sense that a Java stream is terminal, in the sense that that's actually initiating the whole thing and starting it. In this case, it's just whatever is the last thing in the Fluent chain of operations. Any other questions about any of that stuff? All right, so I told you that we had a couple different variants of these methods. We have the non-async methods and the async methods. The async methods run in this particular case, in the common, well, they run in the common fork join pool, or they run in whatever pool was given as the pool for the initiation of all this stuff. So we'll take a look in more detail about all these different methods in a second, or most of these methods in a second. But these are ones that only run after the completion of a single previous stage. There's then a bunch of other methods, and once again, there's both non-async and async variants that run at the completion of two previous stages. So you can think of these as essentially a logical AND operation. So, for example, then combine runs when both of two completable futures have finished. And as the name suggests, we then combine the results. And we'll see there's some other things here that we'll look at as well. Once again, I'm not going to go through this chart in detail, but they take different kinds of parameters, they return different kinds of results, and they have different kinds of behaviors. And the third and final type of completion stage method, of which there are again multiple variants, will complete when either of two previous stages complete. So this one here, the previous one, completed when both of two previous stages completed, whereas this one will run when either of two previous stages complete. Yes? Great question. Yes, you can have an AND of more than two, and you can have an OR of more than two, except those are what are known as arbitrary arity methods, and we'll cover them in a second. They're more complicated. They're simpler in one sense because they don't get as carried away as all this stuff, but they're also more complicated for reasons we'll look at later. But yes, you can also wait for multiple things, either the conjunction of multiple things or the disjunction of multiple things. There's also ways of doing that. So now that I've given you kind of the Cliff Notes version, just so you get your head around the fact that there's all these different variants, let's take a look at some of the key methods. And these are methods you'll need to understand, at least some of the methods you'll need to understand in order to implement the final assignment. So the first one we're going to look at is really very simple. It's called then apply. And as you can see, here's its signature. It will apply a function actions. This is a function action to the result of whatever the previous stage was. That's its job in life. And it returns a completable future that, when complete, will contain the results of the action that's run, that's given here as the parameter. We typically use then apply for synchronous actions that return a value, not a future. What the heck does that mean? Well, here's an example. This is what we had before. We have our unreduced big fraction. We have our reduced supplier. We say CompletableFuture.supply sync reduce. And that's going to run in the background asynchronously. And when that's finished, we then apply this action, big fraction, : : to mixed string, which, as you can see, is a synchronous action that returns a value. It returns a string. As the name suggests, it returns a mixed string. And so that's going to run, and this will give back a completable future to a string in this particular case. There's another method that at first glance looks an awful lot like then apply, called then compose. And it's got really subtly different semantics. So let's talk about that. So here's then compose. It applies a function action to the previous stage's results. That sounds pretty much like what we just looked at. And it returns a future containing the results of the action directly, as opposed to a nested future. Now again, it may not be entirely clear what distinction I'm making, so I'll show you some examples here in a second. The way to think about this is as follows. If you recall, remember flat map? We talked about flat map in the context of a stream. And if you had say a stream of lists of strings and you gave it to flat map, you'd end up with a stream of strings that would flatten things out, so you wouldn't end up with nested structures. That's essentially what then compose does. So if you were to use then compose and you had two completable futures, you would end up with a single completable future result, as opposed to a completable future to a completable future result, which would be nested. And so we use then compose to avoid nesting. So let's take a look at an example that'll hopefully make this a little bit more clear. So let's assume we have a variable called reduce and multiply fractions. And this is going to be a function that takes a big fraction and a completable future to a big fraction. And it goes ahead and it will asynchronously reduce the unreduced big fraction that's passed to it. Okay, so far so good. And let's say that we then go ahead and say then compose. So we run this thing asynchronously. This is going to give back a completable future to a big fraction. And then we compose that, which means it'll run after the asynchronous operation is finished doing the reduction. And we're going to take the reduced fraction, and then, in this case, we're going to go ahead and asynchronously take that result and multiply it by something else. So what's important to note here? Well, supply async returns a completable future. If we were to use then apply like this, we would end up with a completable future to a completable future, because they would nest, because we know that then apply returns a completable future to whatever the result of the action is, and this particular action returns a completable future. So we'd end up with a completable future to a completable future, which is doable and it works, but man, oh man, is it verbose and unwieldy. So instead, we use then compose, and what then compose does is it kind of strips off the additional nesting, and you'll end up with just a completable future when we're all done. So it's a way of avoiding nested futures, which is unwieldy. So that's one way to do this. There's yet another way to do this, which is to apply the async variant of then apply. So then apply also has an async variant, which will go ahead and run this particular lambda expression in another thread in the fork join pool, and it'll return a completable future to the result. So you can either do code like this, using then compose, where you run supply async asynchronously, or more succinctly, you can just say then apply async and get the same result. So then apply async can often be used to replace then compose supply async nestings. So I like this approach much better. There's another, I'm just going to mention this as a little side note. You don't have to know it in detail, but if you have an operation that runs asynchronously and returns a completable future, you can use then compose with the function identity method to strip off the nesting. That's another way to avoid having deeply nested completable futures. All right. Or you can run the code like this. You could just go ahead and use then compose async. So there's just a bunch of different ways to do these different kinds of operations. All right. So that's then apply and then compose. For your upcoming programming assignment number 4, you'll have to use those methods in various ways, or be familiar with how they work. The next method is then accept. And then accept is a little different from the previous two in a couple ways. First, it takes a consumer as opposed to a function. That's not that big of a deal. Except this consumer is going to act as a callback. So there's going to be some kind of operation that gets done on this particular consumer action. And the return value of then accept is a completable future to void, which means there is no return value. So one of the consequences of this is you really only want to use then accept at the end of a chain of completion stages. So what you see here is we started doing this reduction asynchronously. When it finished, we applied this big fraction to convert it to a mixed string. And then the last thing we do in the stage is we go ahead and print the result. So there's no return value from then accept that's meaningful, unlike supply async and then apply. Instead, we simply pass it an action that has a side effect, which in this case prints the result. And that's what the side effect is. You have to be very, very careful using then accept, because you can end up with something that's known as callback hell, where you have this very heavily nested code that has callbacks after callbacks after callbacks and so on. And you can read this article about callback hell. This is a big problem with some variants of JavaScript if you don't use the more advanced features properly. And the same thing holds with completable futures. You should use then except extremely sparingly, if at all. All right, so those were some of the methods that work with the completion of a single previous stage, right? So then except gets called when whatever completed ahead of it. Then compose gets called whenever whatever was in front of it completed, et cetera, et cetera. So those are a single completion. Then combine, in contrast, is triggered when both of two previous stages run. And in this case, you can see that what it takes is a by function that will take the results from both of the previous stages and do something to it. And it returns a future that contains the results of applying the by function action to the results of the two previous stages when they complete. So you can basically think of then combine as performing a reduction. So it's a little bit like collect in a way. It's a very simplified variant of collect or reduce or something like that. I'm using that very metaphorically. It just gets the results and turns two things into one. Here's a real fun example that illustrates how you might use this. In this case, we have two completable futures, CompF1 and CompF2. As you can see, they do separate things. The first one will multiply two big fractions together. The second one will divide two big fractions. And then we take the results from the first computation that's running asynchronously, and we combine it with the second computation that's running asynchronously. And when both of these computations finish, successfully of course, we then go ahead and add the results together. So this big fraction add only runs when both CompF1 and CompF2 complete. And then we print the results or whatever. The point is that we don't do this computation, the big fraction add, until both of the previous computations are finished. So it's basically a logical and. Then the third and final type of completion stage method is one where something is triggered by the completion of either of two previous stages. So this is kind of the, make a choice, the red pill, blue pill, which one do you want, right? You have to accept one of the two. Anybody here ever see The Matrix? Do you know what the red pill, blue pill? What would happen if you ate both, right? No one ever, they need to write a sequel where he eats both. So in this case, we're going to take a consumer action that'll handle either of the previous stages, whichever one finishes first. And this one returns, in this particular case, a future to void. So as a result, it's often used at the end of a chain of completion stages. So let's take a look at a really fun example. We'll look at this in more detail later, but I just want to foreshadow it now. So as you guys undoubtedly know, especially if you've taken data structures and algorithms class, there's different types of sorting algorithms. You've got quick sort, you have merge sort, you have shell sort, you have bubble sort. There's all these different kinds of sorting algorithms. And if you remember your asymptotic time complexity analysis discussions, different algorithms tend to work better on different kinds of data. So some things work really well if the list is, the input's almost already sorted. Some things work well no matter what. Some things work well, it just depends on if the adversary arranges the data in a convoluted way, then quick sort won't work very well. If you don't do it right, blah, 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 blah. So back in the old days, people spent a lot of time, sweating about which of these sort routines should we use? Should we use this one? Should we use that one? Well, in the brave new world we live in now, where there's more cores than we know what to do with, the obvious solution to this problem is not to sit there and do some kind of mathematical analysis to figure out which is the best one to do. Just do them all. And whichever one finishes first, take the results, right? Why not? You got cores galore. So what we're going to do here is we're going to have a list, and we're going to go ahead and we're going to asynchronously quicksort the list, and we're going to go ahead and asynchronously merge sort the list. So we're going to use both sort routines, start them up running at essentially the same time. And then we're going to say, accept either of the results that finish first. So if quicksort finishes first, we'll take the results from quicksort. If merge sort finishes first, we'll take the result from merge sort. What's not to like, right? Why make a choice, right? So in this case, we'll use except either, which will take whichever one finishes. And so we'll see in a second, this will print the results out from whichever sorting routine finished first. Oddly enough, or perhaps not so oddly when you think about it, except either doesn't cancel the other operation that's running. It just selects the first one, and the other one just finishes, and then the results are thrown away. And there's various reasons for that, not the least of which is these asynchronous operations can actually be used in multiple places, and so there may be some other part of the program that wants the results of that other computation, even if this particular part doesn't. Okay, so that's the end of the second part of the Completable Futures advanced features discussion. I think you'll probably agree that the mechanisms we talked about here are much more powerful than the basic Completable Future variants and way more powerful than what we had talked about earlier when we were discussing vanilla Java 5 futures, which had all kinds of limitations.